Hello students, let us study about group 18 in p block elements. So group 18 elements are otherwise called noble gases. They are helium, neon, argon, krypton, xenon and radon. So radon is a radioactive element. So helium, neon, argon, krypton, xenon and radon. So these are group 18 elements. So let's see the occurrence. So all noble gases occur in atmosphere except radon. So except radon, all noble gases occur in atmosphere. Radon is actually a decay product of radium, Ra. So we can write Ra gives Rn plus He, helium. So helium is also formed. So we can write the atomic number and mass number of helium. So with this we can write the other atomic number and mass number. So it is 2, 4, then comes 6. Instead of 6 we can write 2, 2, 2. Then 2, 4, 6. Then we can write 8, 8. Then 88 minus 2 it will be 84, 222 plus 4 it will be 226. So in this way you can write the atomic number and mass number of these elements. So radon is the decay product of radium. So this is about occurrence. Now let us see the electronic configuration. What is the electronic configuration of noble gas or group 18 elements? Electronic configuration. So for helium, we know it is 1s2 configuration and this is called a duplet configuration. So from neon, we can write the electronic configuration and we will get the outer shell configuration as 2s2, 2p6. Then comes 3s2, 3p6, 4s2, 4p6, like that. So we can see there is octet configuration. So octet configuration is there for other elements except helium. So helium is an exception. It is having 1s2 configuration and a duplet configuration. So others are having octet configuration. So the general electronic configuration of group 18 is ns2 np6. So there is ns2 np6 configuration for group 18 elements. So we can say there is completely filled electronic configuration, or it is a stable electronic configuration. So there is no tendency to gain electrons or no tendency to donate electrons. So it is having a stable electronic configuration. There is no tendency to gain electrons or no tendency to donate electrons. So that is about the electronic configuration of group 18 elements. Now let us see the atomic radii. So in the case of atomic radii, like the other groups, the atomic radii increases down the group. So atomic radii increases down the group. So down the group we have already studied atomic numbers. Atomic number is increasing, number of shells are increasing. So atomic radii also increasing. So down the group atomic number is increasing, so number of shells are increasing and atomic radii also increasing down the group. So this is about atomic radii. Then comes ionization enthalpy. So ionization enthalpy. So we have seen it is having a stable electronic configuration. Since it is having a stable electronic configuration, the ionization enthalpy will be very high. So noble gases are having high ionization enthalpy since it is having a stable electronic configuration. So down the group ionization enthalpy decreases since atomic radii increases down the group. So anyway, down the group ionization enthalpy increases since atomic radii is increasing. But there is high ionization enthalpy for noble gas elements. Then comes electron gain enthalpy. Electron gain enthalpy. Electron gain enthalpy. So we have already seen there is no tendency to gain electrons. So since it is having stable electronic configuration. So there is stable electronic configuration, no tendency to gain electrons. So but if we need to give an electron to the atom, we need to give extra energy. So extra energy is to be given. So we can say energy is absorbed in this case. In this case, energy is absorbed, not released. Since it is absorbed, it will be a positive value. So if it is released, we will see it is a negative value. Since it is absorbed, it is a positive value. So we can say it is high positive electron gain enthalpy for noble gases or group 18 elements. So since it is having a stable electronic configuration, no tendency to gain electrons. But if we need to give an electron to the atom, we should supply some extra energy. That means energy should be absorbed. So energy is absorbed, it will be a positive value. Electron gain enthalpy will be a positive value. So we can say there is high positive electron gain enthalpy for group 18 elements. Now let us see the physical properties. Physical properties. First point is it is monoatomic in nature. It is monoatomic. Then colorless, odorless, tasteless. Then it is sparingly soluble in water. Then it is having low melting point and a boiling point. So these are the important physical properties of noble gases. It is monoatomic in nature. Colorless, odorless, tasteless gas. It is sparingly soluble in water, low melting point and a boiling point. So we can expect a question from this part, that is noble gases have a low boiling point. Why? Why there is low boiling point? Why there is low boiling point? So since it is monoatomic in nature, the interatomic attraction is due to weak dispersion force. So there is a weak force between the atoms. So the interatomic attraction is due to a weak dispersion force. Since the force of attraction between the atom is very weak, there is low boiling point or low melting point. So this is the reason. Then comes the chemical properties. Actually, noble gases are inert. Noble gases are inert in nature, or they are least reactive. Noble gases are actually inert or they are least reactive. That is another question. Noble gases are least reactive, or why they are called noble gases. So, they are least reactive in nature or they are inert in nature. So the reasons are they are having a stable electronic configuration, that is NS2 NP6, that is a general electronic configuration. Then high ionization enthalpy, then high positive electron gain enthalpy. So because of these three reasons, noble gases are inert or least reactive in nature. Or why group 18 elements are called noble gases? The answer is the same. Stable electronic configuration, high ionization enthalpy and high positive electron gain enthalpy. So because of these three reasons, noble gases are least reactive in nature. But there is a scientist called Neil Bartley conducted an experiment, that is Neil Bartley or N. Bartley. In his experiment, he reacted oxygen and PTF6 and he found a compound like this. It is a red compound. He found a compound like this. And he found that the ionization enthalpy of oxygen is similar to xenon. So xenon and oxygen is having the similar ionization enthalpy. So ionization enthalpy of oxygen and xenon is similar. So instead of oxygen, he reacted xenon and PTF6. And he found a compound, a similar compound like this, that is XCPTF6. So this is again a red compound. He found a compound like this. So with this discovery of a xenon compound, more xenon compounds are discovered in the laboratory. Xenon compounds are discovered later. So first one is xenon with the PTF6, xenon XCPTF6, that this type of compound is formed. So Neil Bartley conducted an experiment at first with oxygen and PTF6. He found a red colored compound like this. So he found that oxygen and xenon is having similar ionization enthalpy. So that is the main point. So since these are having similar ionization enthalpy, he carried out an experiment with xenon instead of oxygen. So he again found a compound similar to first. So with this successful discovery, xenon compounds are again discovered. So xenon is actually form compounds with the fluorine and oxygen, since they are electronegative in nature. Fluorine and oxygen are electronegative. Xenon forms compound with the fluorine and oxygen. So more xenon compounds are discovered later. But this is the first experiment. Then there is a question: what inspired Neil Bartley to carry out the reaction between xenon and PTF6? The point is the ionization enthalpy of oxygen and xenon are similar. So this is the point, and this inspired the scientist to carry out an experiment or the reaction reaction between xenon and PTF6. So more xenon compounds are discovered later. Actually xenon forms compound with fluorine and oxygen. So we will see xenon compounds in the next class.